So far, we've learned about knowledge graphs. We know what they are. We've also learned about approaches for identifying or creating these knowledge graphs. We talked about, expert designed knowledge graphs. We also talked about using machine learning and very basic approaches like Q matrices to create the knowledge graphs. But today we're going to work with a few of the hybrid approaches that have been used. One of them is partial knowledge spaces. And then we also have learning factors analysis, which I will provide a video for. Make sure you watch that video. It's in the resources, as well as the learning curves. That video was created by Dr. Ryan Baker. It's well, presented. I want you to just watch that and get the most out of that. But I want to focus on partial order knowledge spaces. Partial order knowledge spaces are a very specialized form of knowledge spaces. To understand what a knowledge space is, which was proposed by Falmani et al. In 1990, we need to understand what a knowledge state is. Falmani and co. define a knowledge state as the set of all questions that a student is capable of solving for any given domain. All the questions that the student is capable of solving for any given domain is referred to as a knowledge space. Now, if you put these knowledge spaces or knowledge states together from all the students who have actually learned the domain or know about the domain, that creates what's referred to as a knowledge space. Desmarais proposed what we refer to as a partial order knowledge space or knowledge structure, in which he suggests that there is a relationship between the items that a student knows how to answer, or the items in a knowledge space. That relationship, he says, is a prerequisite relationship. Hence, if you're able to answer or master one of the questions right, which is the prerequisite, then you should be able to master the other question right? That specifies a prerequisite relationship. Let me show you an example in the next slide. In the next slide, and this example is from Desmarais et al. 2006. There are 4 items here, items A through D. Item A basically requires a number of skills, right? You cannot succeed at answering item A if you do not know how to answer steps B, C, and D, or items B, C, and D. If you cannot answer them, you cannot answer, or a student cannot answer item A. Inversely, if a student cannot solve question D or item D right, they cannot answer any of the questions in the set, which presupposes that there is some kind of a prerequisite relationship between item D and item A. Of course, items B and C don't tell us much, because if you can answer item B, there is no guarantee that you can answer item C, right? So there isn't any such relationship between the two. However, there is a relationship between item D and the other items in the structure. And, inversely, A2 has B, C, and D as prerequisites to be able to answer item A right. With this in mind, you can tell that we can easily extend this to skills, right? So instead of items, the items can become skills. Take, for example, item A in elementary school math could be addition of mixed fractions. Look at item D. Item D could be giving a name, right? So each of these will become knowledge components or skills, which can then be put together in a knowledge graph. Remember that probabilistically, we can add more items to this or more skills to it and figure out how well they predict students' data or student performance. and then expand upon the graph and even clean it further. So POGs, partial order knowledge structures, can also be extended to skills. All right. So now we know partially about how POGs works.